Hey everyone, welcome to this explainer. Okay, so have you ever looked in a mirror and just kind of wondered what it would be like if your reflection suddenly stepped out into the real world? Well, in chemistry, that concept isn't science fiction, it actually happens. Welcome to the mirror universe of molecules. Today, we're demystifying optical isomers. We're going to explore the absolutely fascinating mystery of chemical evil twins. See, on paper, these molecules look completely 100% identical, but in 3D space, they act entirely differently. All right, here is our game plan for today. First up, the mirror universe of molecules. Second, spotting a chiral center. Third, bending plane-polarized light. Fourth, the racemic mixture twist. Fifth, biological optical isomers. And finally, acing your chemistry exam.
Okay, let's dive right into part one, the mirror universe of molecules.
I really want you to just picture this for a second. What if a molecule actually had a mirror image twin? Like, imagine two molecules that share the exact same chemical formula, the exact same physical properties, like melting point, density, all of that, but somehow they behave completely differently in certain situations. How is that even possible? Well, the answer is something we call an enantiomer. Basically, an enantiomer is a specific type of stereoisomer, where molecules are non-superimposable mirror images of each other. The absolute best way to wrap your head around this is to look at your own hands right now. Your left hand and your right hand are perfect mirror images, right? But try placing your left hand directly on top of your right hand, palms facing the same way. They don't overlap perfectly, do they? Your thumbs stick out in totally opposite directions. They are what we call non-superimposable, and these special molecules do the exact same thing in 3D space.
So what makes these enantiomers so incredibly tricky? Well, they share the exact same molecular formula, the exact same structural formula. If you try to boil them, melt them, or check their density, those physical properties are identical. And that's exactly what makes them so hard to spot. They are physically identical twins in almost every single way, except for one very special mind-blowing superpower involving light. But before we get to the light, we really need to know how to locate them first.
Which brings us to part two, spotting a chiral center. Okay, so here is the golden rule for finding our hero, the chiral center. We'll break it down step by step using the molecule 2-chlorobutane 1-ol. A carbon atom is chiral if and only if it is bonded to 4 completely different groups. Step 1, find your central carbon. Step 2, check out the first group attached, which is a hydrogen atom. Step 3, check the second group. We've got a chlorine atom. Step 4, a methyl group, CH3. And finally, step 5, the fourth group is CH2OH. Look at that, 4 totally unique attachments. Because all 4 groups are different, this molecule has absolutely no plane of symmetry. It is officially chiral, meaning it exists as 2 enantiomers.
Let's quickly test this with another classic example, CHBrClF. Just look at the central carbon. What's it holding on to? A hydrogen, a bromine, a chlorine, and a fluorine. 4 completely distinct groups. Bam! That automatically guarantees chirality. It's really that simple. Whenever you're evaluating a molecule, just count the unique groups. If you hit 4, you've found your mirror universe twin maker.
And this brilliantly illustrates why this matters, bringing us to part 3, bending plane-polarized light. Okay, to understand their superpower, we kind of need to talk about light for a second. Normal light is just vibrating everywhere, in all possible planes. It's messy, it's chaotic, but when you pass that light through a special polarizing filter, it gets organized. It comes out vibrating in just one single plane. This is what we call plane-polarized light, and it's the exact tool we use to test our molecules. This is where we actually see the physical difference between our left and right-handed enantiomers.
Now, here is where the magic happens. When we shine this plane-polarized light through our enantiomers, look at the comparison. If you have the dextrorotatory, or positive enantiomer, it actually grabs that light and rotates it clockwise. But if you have its mirror image twin, the levorotatory, or negative enantiomer, it rotates that exact same plane-polarized light anti-clockwise. Left-handed and right-handed molecules bending light in absolute opposite directions. How cool is that?
But what if we mix them? That brings us to part 4, the racemic mixture twist.
Now, what's really fascinating here is what happens when you throw both the left and right hands into the exact same space. Imagine we create a perfect 50-50 mix, a racemic mixture containing exactly 50% of the positive enantiomer and 50% of the negative enantiomer. You've got one pulling the light clockwise and the other pulling it anti-clockwise with the exact same force.
The results? They totally cancel each other out. Even though the mixture is completely packed with these optically active molecules, the racemic mixture as a whole does not rotate plane-polarized light at all. Zero overall optical activity. It is a perfect chemical stalemate. Let's ground this abstract chemistry in reality a bit. Part 5. Biological optical isomers.
So, if we look at the ultimate building blocks of life, amino acids, most of them, like alanine, serine, and valine, naturally contain a chiral carbon atom. They naturally show optical isomerism. But you know chemistry, there's always an exception. And the big one you really need to know is glycine. Look closely at its formula, NH2CH2COOH. The central carbon in glycine is attached to an amine group, a carboxyl group, and 2 identical hydrogen atoms. Because of those twin hydrogens, it totally fails the chiral test. Therefore, glycine is not optically active.
All right, let's pivot to Part 6, acing your chemistry exam.
We've got to prep you for the boss fight here, so let's dodge the traps examiners absolutely love to set. The crucial point is knowing exactly what not to do. First, please do not assume every carbon with 4 single bonds is automatically chiral. It's not about the bonds, it's about 4 different groups. Second, forgetting that if you spot 2 identical groups like those hydrogens we just saw in glycine, there is no chiral center. And third, confusing geometrical E/Z isomerism with optical isomerism. Remember, optical isomerism is all about those non-superimposable mirror images. Okay, here's your ultimate cheat sheet to make sure you have this locked down. Let's rattle through it dynamically to lock it all into place. The type of isomerism, stereoisomerism, the name of the isomers, enantiomers. The strict requirement, a chiral carbon with 4 unique groups. Their relationship, non-superimposable mirror images. And their effect on light, the positive isomer rotates it clockwise, the negative rotates it anti-clockwise. And a perfectly balanced racemic mixture gives you 0 overall rotation. Boom. Let's seal this with the formal exam-style definition. Optical isomers are stereoisomers that are non-superimposable mirror images of each other and rotate plane-polarized light in opposite directions. Seriously, if you can just commit that single sentence to memory, you have successfully nailed the core of this entire topic. As we wrap up this explainer, I want to leave you with kind of a wild thought. We know these left and right-handed molecules act completely differently with light, right? But how do these uniquely shaped molecules interact with the highly specific 3D biological receptors inside your own body? Think about it. If a biological receptor is basically a lock, what happens when you try to shove a mirror image key inside it? The implications for medicine and human biology are absolutely massive. Keep that in mind as you continue your journey through biological chemistry. Thanks so much for joining us, and keep learning.